Hey, Matt Rogers, I'm with WSC, as David mentioned. We've been working with Fargo staff and the ABC team on the Fargo project with planning and design. So yeah, David mentioned I'll be presenting a summary of the preliminary pilot facility water quality testing. Some of you board members may have seen that during last summer's open house. So we'll go through an overview of what we did and the results and a little bit about next steps. Can everybody hear me okay?
No.
Here we go.
How about now? Better? Yeah, holler at me if you can't hear me. So we'll be going through, again, the water quality summary. We put that right up front, so we don't need to wait for that to present the results from a water quality perspective. Then we'll talk a little bit about the purpose and objectives of the pilot, the background of what we operated, a little bit of context for why we had to do the things we did as far as technologies that were out there. We'll go through the piloting sequence, which was done in 2 phases, talk about the methods for data collection, revisit those results in context of some key findings, and then again, go through next steps for the next phase of the project and how we leverage what we did during piloting for future design efforts. So for the water quality summary here, just to orient you to the table, we're going to go through line item by line item here. These are the key system drivers I'm going to be highlighting here by constituent. We have in the middle column, just for context, some comparison to what the drinking water objective is for these particular constituents. Our anticipated permit objective to replenish Big Bear, and then the results. On the bottom left there, you'll see a couple of notes. Now we're presenting these in parts per million. Probably being on drinking water consumer reports can also be about milligrams per liter if they're equivalent. And these results are based on the footnote 2 there, the C0 effluent, which is closed circuit reverse osmosis during the phase 2 of the pilot. That's just to note that we had 2 different high recovery RO systems that we piloted. 2 different phases. We're using from the latter phase, which was the RO system that performed better and represented what we've achieved through the project. And then I'll highlight, the legend in the bottom right as we go here, starting with total dissolved solids. That green on the far right indicating that we've met the targets. So total dissolved solids, you can think of it as the salts in your water. We have a subset of here we'll present here shortly. Comparative drinking water objective of 500, and our anticipated permit limit was 175 permit objective rather. The treatment result was 8. That's common for a high recovery system. Even a little bit better than we anticipated, so we far exceeded that objective. As a subset of total dissolved solids or TDS, we have sodium. That anticipated permit objective is 20, and we got down to 0.8. Chloride. Drinking water objective comparison of 250 parts per million. 10 is what we anticipated. We got down to 1.1. Sulfate, similarly, 250 for a drinking water comparison, 10 for the anticipated objective, and we got down to nearly 0 there at 0.1 ppm. So these salts, sodium chloride and sulfate, again, are a subset essentially of total dissolved solids. These are treated primarily through the reverse osmosis system. So for what we piloted, the RO really will tackle these 4 constituents. Next, one of the 2 nutrients we focused on being total phosphorus. You'll see there in the second column, ppm as phosphorus, really just to make sure we're talking the same language as the regulators, engineers, et cetera. For different types of phosphorus species, you bundle it into total. For our anticipated objective, we have 0.035 ppm. That's driven by a lake objective. We got down to 0.013, which is essentially the limit of technology for how far you can get down for total phosphorus. The anticipated objective is on par with probably the most stringent phosphorus objective you find in the country. You can't really get much lower again, being at the limit of technology there. The second nutrient we looked at, again, these phosphorus and total inorganic nitrogen being driven by lake objectives. ppm is nitrogen, again, same approach as phosphorus. We have to quantify it on a nitrogen basis since there's several different forms that comes in. Total inorganic nitrogen is ammonia, nitrate, and nitrite. I won't get into the details there, but just for context, the subset of what it includes. Drinking water objective comparison is 10 ppm for total nitrogen. Anticipated objective for Replenish Big Bear being 0.15. This is the one that we did not meet through the pilot at 0.27. And the note there is that design changes are underway to meet the objective. This is also essentially approaching the limit of technology. There are alternatives that we'll discuss later in the presentation of how we can tackle that. We piloted a couple different processes, barriers of treatment for nitrogen, so we'll highlight what we can do moving forward on that. Next is total organic carbon as ppm at 0.5 anticipated limit. We got down to 0.16. Total organic carbon is essentially for this advanced treatment process, as engineers and through a regulator's eyes, a good indication of how well you're treating the water for other surrogate compounds such as CDCs and pharmaceuticals, et cetera. So when we hit that 0.5 number, we're confident using this as an indicator compound that we'll be able to meet those objectives and that we're getting efficacious treatment. Lastly is total system recovery, which we can think of as just for how many gallons you put in to a process, how many gallons are you getting out. So our 98% target there is driven by the need for infrastructure to handle the concentrate or the brine that's left from the RO systems. We achieved 98.7 with both on-site high recovery RO and an off-site brine utilization process. We'll talk a little bit later about maybe some alternatives to tackle that differently and how we might be able to get a little bit higher than that. So again, total system recovery, the 98% is an example. If I put 100 gallons in, I'm getting 98 gallons out. In today's engineering world, thankfully, ROs got much more efficient. Decades ago, it was not uncommon to see recoveries through an RO system of 60 to 70%. With technological advances, we're able to get up to 90% of RO systems, and then further above with additional brine minimization processes. And I apologize, I should mention, board members, feel free to interrupt me at any time if you have any questions.
Everybody has a question on this, but the commit objectives, are those the federal and state standards? Are those, is that the total list of nutrients or constituents that you're looking for under the state and federal permitting process?
No, it's much more exhaustive, as I think you're kind of alluding to. So these, from an engineering perspective, we focused on these ones because these are the main ones that are the hardest to meet with the technologies that are out there, and they're driven by lake objectives and discussions we've had with the regulatory agencies leading up to this point. So we looked at, we'll get into it a little bit later. I think we have a slide of, over 200 different constituents for sample, maybe more. But we have a slide on that to touch on it later. But yeah, to answer your question, there's much more that we'd be looking at, but for the pilot and preliminary design and setting design criteria, and being able to select the technologies that are going to get the job done and meet those limits, these are the main ones we focused on in summaries here.
So you feel fairly confident then by meeting these objectives, then the balance of those other 200 constituents will be just met in that process.
Yes, and we're also presenting for the sake of brevity here too. So we're not only here for 5 hours. The pilot report obviously has more detail on the additional constituents we listed. There's an appendix with some additional results and additional things we did outside of these here.
Thank you. Any questions?
Why go with greater objectives or the smaller amounts, parts per million, than drinking water quality?
Yeah, so it's good to look at that for context. It's really just highlighting how stringent the objectives are for the lake. Both of these limits that you see here in that second to last column are driven by lake objectives, which is really, just set by Santa Ana basin plan process through the regulatory agencies. Alpine lakes like this tend to have more stringent objectives in drinking water quality to protect the beneficial uses of the water body. Yeah, really a reflection lake water quality objectives for the most part.
And the outcome of, well, the quality of the water going out would be higher quality than drinking water is what it sounds like.
For many constituents, yes. I can't say without certainty all of that information in front of me, but most of them, yes. We're well below drinking water objectives for both of these constituents.
Okay. Well, thank you.
Again, feel free to interrupt me at any point.
You couldn't turn your tap on and put that water in the lake. That's the reality is like you couldn't just open your tap up and put it in the lake. You could this, but not that.
Thank you.
And again, we're gonna talk about it later. I just want to reiterate, so it's clear up front. These results will revisit toward the end of the PowerPoint, but that last column is based on phase 2 water quality from the second largest system we have. So for purpose and objectives, what is the pilot, what it isn't, and then what the driver to serve to why we need to do it. For what it is and what it isn't, it is a small scale test of the potential treatment process using the same water source being borrowed secondary effluent. That would be treated through the full scale system. It also provides us the opportunity to collect data to optimize, design, select design criteria for the final treatment process. Estimate that brine production by way of the total system recovery calculation to understand what kind of infrastructure and how much of it will need for brine minimization and handling that brine. And then, importantly, also gaining an operator experience for operators to understand how they can operate this type of process, technology, operational intensity, and work out maybe some of those pain points or benefits of some of these processes to help guide us in what we select. What it isn't, it is not the final Replenish big bear treatment process. We are piloting these technologies based on preliminary engineering of what we felt could get us there. But this was done with the drivers we'll highlight on the next slide to understand what kind of treatment train we need to hit those stringent objectives. It is not water quality summary and this pilot effort, not an exact report on the Replenish Big Bear program water quality that will be discharged in March. Again, it is just helping us really hone in on what the design process should be. And what's not listed here, but it's come up before, I think, in board discussions is this data is also helpful for discussions with regulators. So for the drivers, again, just emphasizing the very stringent water quality requirements that we're up against that are set by the regulations and that basin plan water quality objective. We also have a unique project needs here being an inlet facility that we can't really handle brine as easy as someone down the mountain who has access to a brine line. So this informs the selection of the proposed treatment process. Inform the selection of what will be the proposed treatment process needed to meet those objectives. Very importantly up here from wastewater treatment perspective, cold weather is not good for some treatment technologies, so we have to understand how to fare in a cold weather climate. And then lastly, again, to quantify that total system recovery and estimate that brine to be produced.
How did you duplicate the winter temperatures?
Fortunately, with being able to do a pilot up here, we don't have to duplicate it. We have the direct secondary effluent that would go through the full scale system and arguably more conservative. As you may know, those two big horseshoe ponds out there, that's where the effluent goes before it's pumped to the Cern Valley. So it gets wind blown and exposed to the atmosphere. It's probably going to be colder than what would come directly off the clarifiers and into the advanced treatment process. So it was colder than we may even anticipate for full scale. And being able to use that water source up here being the secondary effluent allows us to directly test that impact in cold weather.
Thank you.
Any other questions? So for some background, we'll talk about what we piloted, and then I'll give some more context around brine minimization, since that's kind of an nebulous topic just to mention without looking at maybe a process flow diagram. So we piloted 4 treatment processes at the Marble site behind us. The pilot ran at about 25 gallons per minute, which is less than 1% of what the full scale system would be, which is around 1,500 gallons. We actually ran more around 15 to 20 based on the condition of the process, but point being, we're around 1% of the full scale flow rate. So we took that secondary effluent and we piloted first sand filters. You'll see in parentheses here, Nexum, which is just alluding to or noting the manufacturer vendor that we selected for piloting. On the site later, this is not what's being proposed or what was selected as manufactured for the full scale system. It's just, we have to pick what's available out there for piloting. So you'll see the full number there, the process, and then underneath the parentheses, the company that provided the equipment. So the sand filters are primarily for nitrogen and phosphorus removal. From there, we go into ultrafiltration membranes, which were provided by DuPont. These provide direct physical pressurized filtration of solids, protozoa, some bacteria, etc. I can skip one version solid. There we go. Next was reverse osmosis, again targeting high recovery systems, which there's not a lot out there in the industry yet that can push to 90% recovery. We had IDE and DuPont for that. IDE in the first phase, second phase, we'll talk about some details about that later. And then for UV AOP, which is ultraviolet disinfection and advanced oxidation process, which was provided by Trojan. From there, we have the produced water. UV AOP is essentially an advanced form of disinfection process. You have UV lamps that can destroy contaminants and microorganisms on its own. But you add oxidants such as like sodium hypochlorite, bleach, or hydrogen peroxide. That UV and that oxidant react to produce what we call radicals. Those radicals are very effective at destroying even further microorganisms and organic compounds in the UV lamp. And then lastly, we had brine minimization, which during the first phase was done by IED. We had to pilot that off-site. The cost of doing it on-site was almost twice as much as sending the brine to IED's research and development facilities to have them test that there. From that process, you're getting the brine from that high recovery RO system. It's coming on the left there. For this particular technology we piloted, we produced pellets that would be either something like the cement industry or disposed. And then from there, that minimized brine stream on the bottom arrow, which that would go to evaporation pond. We'll get into some examples again of the brine minimization step here in a moment. And then we have what would be the produced water arrows showing what's representative of a full scale system. We weren't able to combine the produced water from the brine minimization process back in. So we did not analyze that for a full scale system in the process flow. That's where that would be the areas before subsequent disinfection and advanced oxidation. The little icons that just popped up are water quality sampling points. That's just to note that at each barrier of treatment, we really wanted to understand what was happening through treatment to the specific constituent, so we could help quantify that for our graduate report and our assessment of how the technology is fared and this treatment train worked out all together. And then last, that note that just popped up on the bottom left, emphasizing what I mentioned previously. In parentheses there is the companies that we piloted. Those are by no means what's going to be in the full scale system. They are options, but we selected those based on availability and design criteria, which we thought would be most appropriate for the pilots. You want to circle back on that question? Ready to go back?
It was a case of the 25 gallons a minute versus, you said 1,500.
Yeah, so the full scale system would be around 2.2 MPD, which is around the average annual flow of the facility now. But yeah, we were around 15 to 25 gallons per minute depending on the process. But yeah, the full scale would be around 1,500.
but you don't feel that the processes are time relevant?
Can you emphasize what you're asking there?
I can cook a hunk of meat at a lower temperature if I cook it longer.
Gotcha. Yeah, so the technologies are the same principles, same operational characteristics, same design criteria, just less equipment. So for instance, to answer your question, like reverse osmosis, we may end up with 200 membrane elements, but there's only one. So it's basically the same membrane element in the pilot as it would be in the full scale. We'd have only one versus 200 to get you to that full scale system. So yeah, no perceived difference there. And in fact, you'd probably be able to tune up the full scale system easier than a pilot, because the pilot's not built to be permanent. So you kind of have to deal with some more operational challenges typically. It's gonna accept that this is working again. Okay, that's like it is. Thank you. This slide is just highlighting that we have multiple barriers of treatment for each of these steps that I just went over. Again, the sand filters that are on the far left are primarily for nutrient removal. They do remove some metal solids. Subsequent to that, we have the ultrafiltration membranes, direct filtration of further solids, and then some pathogens. The reverse osmosis system really can handle all these. The only reason solids isn't there is because pretty much all of the particulate solids that are not dissolved are removed upstream. So that includes organics and constituents of emerging concern of the RO system. And then lastly, UV AOP, that ultraviolet advanced oxidation process, takes care of the remaining pathogens, organics, and CECs. And the multiple barriers of treatment for advanced treatment trains are necessary for us because of the stringent water quality objectives, but also through regulatory requirements. We also have to have multiple barriers of treatment for some of these constituents to assure that we have multiple paths and ways of treating this down to the levels we can do. So these next two slides will just highlight a little bit more in the context of why we need brine mitigation. So without it, we have a lower total system recovery. You can recall we were trying to target that 98% total for the pilot and for the full scale. So to just provide an example here, if we've got that 1,000 gallons of effluent coming into a reverse osmosis system, we get 900 gallons of treated water out for a 90% recovery, which go to a discharge point such as Stanfield Marsh. We'd have that 100 gallons of brine, that 10% of that 1,000 gallons that we'd have to manage and deal with. That's our 90% total recovery. And that requires infrastructure. In this case, we're looking at evaporation ponds. So we're noting here we need more evaporation ponds with a lower total recovery. That brine would ultimately have to be disposed of off-site all the way. If we go to brine minimization process, which allows for a greater total system recovery, in this example, we take that 1,000 gallons of influent, we get the 900 out, we're left with that 100 gallons of brine that we need to manage. If we use a brine minimization process like the one we piloted, we can recover more treated water. In this case, that 80 gallons gets us to that 98% total recovery. And at the bottom there, you see that 20 gallons of brine versus the 100 gallons we initially had to deal with, allows for less infrastructure to have to manage that brine, and therefore less to the haul out.
Maybe the question.
The brine minimization, has it been analyzed as far as cost? I'll say, so it's more efficient cost-wise as well, as opposed to having 3 evaporation ponds and hauling off the dry brine.
Yeah, so it is in the project, has always been in the project cost estimate, the brine management and minimization. As far as the analysis of evaporation ponds versus the brine minimization, I would imagine that more evaporation ponds may be cheaper to construct. It may change if you have to acquire more land, but up here, in addition to having the challenge of not having a brine land, we also have the challenge of not having a bunch of land. And we also want to minimize that footprint of evaporation costs for environmental reasons as well. So I don't think a direct analysis of that cost comparison to that. I imagine the brine installation is more expensive. But we do it because it provides more benefits, it's easier to manage, less land we need, and require, allows us to recover more water for beneficial use relevant to the lake.
Ray, did you have something you wanted to add to that? I saw you nodding.
I'll just add, I think Matt covered it, but, we are concerned about the feasibility of being able to evaporate the, the 100 gallons of rain in this example on the mountain. And so really, that's another reason that we're willing to do that down, because if there's not enough space and months of evaporation here, then you have to have, additional facilities to pipe it down the mountain and have supplemental evaporation facilities in Western Valley. And that would actually significantly increase the project cost if we had to go that route. So incorporating brine mineralization provides you with more operational kind of certainty as well. And potentially stabilizes those costs.
And I hadn't considered the weather, so we're talking about winter weather. Not any storms coming through, the colder weather where evaporation not take place as quickly. Thank you.
And that's factored into the amount of acres that have been identified for brine evaporation within the EIR. That there are limited months, and some of those months would actually contribute. Rain.
I don't remember quite how you worded it, but I got the impression that this brine mineralization was the system you're now abandoning.
Yeah, we're looking at an alternative process, that could get us to a higher recovery, potentially for cheaper.
So these numbers are the one that's not going to be used.
The recovery that we were able to attain at 98.7 is the one that we are looking at alternative, but we can't confirm now that it will not be used, but we'll get into a little bit later. We looked at an alternative process using brine from the phase 2 RO system and did some bench scale testing using a softening process, which is a more established technology. And again, may require less infrastructure, meaning less cost, but getting more produced water out. So we're able to essentially pilot both, but one at a smaller scale for bench scale testing.
Basically, the one we piloted was very effective. It works. We think there might be better options, so we're looking into that. If those options that we think might be better don't pan out, then we can also go back to the one that we piloted because we did prove that it works. So that's something that we'll be evaluating throughout the next few months. And that determination will be made and documented in the PDR, which will be completed in the fall, and we'll present that to you at that time.
And then at some point, I asked about the life of the ponds, and I got the impression that you figured this pond will last 100 years.
100 years, yes.
Okay. But that's also assuming the old system.
It's actually relevant, the ponds themselves, so it's the recovery rate itself is the controlling factor, not so much which system we go with. It's actually based on the minimizing the amount of flow that goes into it.
But when we're talking about cost of having to do something with the brine distillate, it's still a case then of you shouldn't have to haul anything off for 100 years.
That was the estimate that was put into. That was what the estimate was put into the EIR and the calculations that were done, and it was based on I think it was it 27 acres?
Yeah, but
It was either 27 or 15, yeah, I think it's 27 acres. And that's what the estimate was done, that we wouldn't have to haul it off too frequently, and they thought it would last, would last about 100 years.
Yeah, I think the takeaway there is the life expectancy of the pond where you would need to repair and replace the liner is shorter than the time period that you need to haul the brine. So just for an example, pond liners and the evaporation pond expected to collect is 50 years, we won't have to haul away the brine anywhere near that, it'd be much later. And that's because we're able to get to that 98%, so it's less brine we're putting in. That brine will stay in there, for a long time before we have to deal with it.
Thank you.
I think that answered my question, I guess, just out of curiosity. You're looking at the 2 million gallons a day, it's 2% or less, but say 40,000 gallons. What does that mean? This is evaporation pond right now, how much water does that add to? How much is that? You ever done that? Did you have just a minuscule amount of that area?
I think we got it in at like 50 gallons a minute. I think that was the number when we did some quick calcs on how much water based on the 2 million gallons a day and that flow rate of 1,500 gallons. I think it would turn into about 50 gallons a minute.
And that's spread out over 27 acres, is that what?
That's correct. So it's, I mean, again, there's a lot of other calculations that go involved in weather conditions and sun exposure and all those other things that go into those calculations that determine how big that evaporation pond has to be.
Correct, and we use the evaporation data consistent with how Big Bear Lake calculates their evaporation, but we've also got an evaporation pan on site here to get site-specific data as well, which will help us further improve the accuracy of our estimates for the acreage that we need. And of course, we have a safety factor for that as well, to make sure we've got adequate space for really wet winters and redundancy if we need to take a pond offline.
So does that, is that really, or maybe that question, is that just going to be one big pond, or you say series of ponds?
You'll have multiple, so you can go between them, that you didn't have that redundancy, yeah, and then it helps keep it shallower, which helps with evaporation.
Yeah, thank you.
Was there any consideration in working on these numbers? Sandy asked about protecting the birds against the salt ponds, and the discussion about whether it's going to be screening or tarps. When you cover your evaporation pond with a tarp, it would seem that's going to thoroughly skew your evaporation rate.
Correct. Yeah, the mitigation measures that we'd have to consider and implement would have to preserve the ability of evaporating ponds. Right. So it would be something different than tarps potentially that would actually allow wind and sun to get to it to allow it to evaporate. Correct.
Thank you.
Any other questions on this one? Okay, so for the pilot sequence, we went through 2 phases, which were primarily split to allow us to pilot 2 different high recovery harvest systems. For phase 1, the same process flow diagram we went through earlier, just highlighting in that dashed box there, the IDE full flow reverse osmosis system. Again, one of the few high recovery harvest systems that are out there available for piloting. And then in phase 2, the sand filters went away. We had limits on how long the structure we were able to now build on site pilot. We also wanted a good opportunity here to get nutrient removal just through the treatment train without upstream nutrient removal, and allow us to do piloting of the closed circuit reverse osmosis system, which should save DuPont those parentheses there, but C0 is the abbreviation. So we had the DuPont ultrafiltration membranes followed by DuPont C0, and kept that same UDA unit there as well. So arrows note popped up here, just again, a reminder of that first slide with the results. This phase 2 is where those results are pulled from for the C0 system, which performed better than IDE GFRO system for the piloting phases. And then again, what's noted in parentheses there, just the equipment suppliers used for piloting, not necessarily the ones who looked up with triple skin. for data collection methodology and the approach we took for gathering all the sampling of water quality analysis that we performed. We went to a certified third-party water quality testing lab called Bureau Fence down the mountain. We analyzed over 200 constituents for the pilot report. That totaled 3,000 blood samples analyzed for 5 sample points. We also did some testing through Barwell's certified wastewater and water quality testing laboratory, mainly to help with understanding the day-to-day operation of some of these processes, but also to collect supplemental data for our analysis. Built up real-time and continuous monitoring of various constituents from this pilot equipment. The same type of continuous monitoring instrumentation that would be in the full-scale system that's reading every fraction of a second or every second to give us an indication of the integrity of the process and how it's performing. And then lastly, a couple pilot process performance tests specific to the ultrafiltration membranes and the UV system. So this data collection group here and methods allowed us to gather the data you see in the pilot report, allow us to do the analysis for presenting here today. You have a question, Greg?
Does the testing of the staining tell you the lifespan to expect?
Are you referring to the staining of the RO membranes? In a way, yeah, it tells you how aggressive that water was on the membranes. And yeah, you can get a sense for if their expected useful life estimates for those particular technologies are on par with what we're actually seeing. So you probably saw maybe even some of the, I think we included some of the specific images, microscopy images. So yeah, it helps you understand what type of scaling, what type of biofouling you're getting on those membranes. Helps you understand what, again, the aggressive nature of the constituents that are coming from the ultrafiltration membranes and then also. So yeah, it does give you an estimate of expected useful life and how.
And then is it projected that the real-time and continuous monitoring would not end with this pilot, it would continue day-to-day operations?
Correct. Even
And
more
would it
so.
be in-house or have to be shipped off?
I mean, I think there's still some of the testing will be done on site, but some will still be shipped out.
Yeah, so you have, I think you may be talking about 2 different things here. So you'll have, from the regional board, your permit enforcement authority, Santa Ana Region Board in this case, they'll have requirements for either daily, weekly, or monthly sampling that you need to perform using certain EPA approved methods. You have to meet certain QC requirements, such as John and his team do now, for the existing facility. So you'll have those permit requirements. Those would be a third-party accredited lab. Barlow may do their own for operational monitoring or for reporting. Again, Barlow's lab is accredited for wastewater analysis, so there's some constituents they can analyze and report on. But for the monitoring, that's like on board the equipment that's provided with it, and that has real-time data outputs that go to their screens in their operator rooms that allow them to see the performance on a real-time basis as well.
And then would we be trying to meet Fish and Game according to the permit, or the Fish and Game's specified standards of what goes in the lake and marsh?
Yeah.
Yeah, we will, absolutely. We have to meet those objectives that are set for us. That's our job, to make sure the treatment process we come up with meet those objectives. Fish and Game does not have any regulatory authority over discharge in the lake. It would be the Santa Ana Regional Water Quality Board.
That's what I was gonna be. Yeah, the reason, it's the regional board that dictates exactly what the discharge requirement's going to be. And so that's who monitor all of that. Fish and Game, I mean, and then those are set based on to protect the beneficial use of the lake, and habitat and all those are all set that way. So it's not Fish and Game, it's actually, an NPDS permit from Santa Ana Regional.
Fish and Game has expressed no concern about what we put in the lake.
I mean, Fish and Game has expressed concern, maybe, to.
So the water quality constituents that Fish and Game would be concerned about to protect the aquatic life are incorporated already into the Santa Ana Basin Plan. And so it's, as David mentioned, the Santa Ana Regional Water Quality Control Board is the responsible regulatory authority. And their regulations incorporate basically the interests of Fish and Game through beneficial uses, which include cold water, aquatic habitat, warm water, aquatic habitat, recreation. So that's the way that that those resources are protected.
So as long as we keep Santa Ana happy, Fish and Game is protected.
Correct.
Yes. And happy.
Thank
Good
you.
question. Yeah, thank you for clarifying that. So to revisit the pilot results, we presented that first slide, present some key findings here. We'll revisit those drivers and results here. And then look at some of the water quality monitoring results and what that means for future design efforts. So again, this is the slide we went over earlier, just highlighting CIN is the only one we didn't meet. We'll talk a little bit here in a moment about how we're going to tackle that and what's already underway there. But the takeaway here is the pilot performed very well against the objectives we set, far exceeded a lot of them. And the key one that we're looking at pre-pilot was the total phosphorus, and that 0.035 ppm approaching of the technology that we're able to meet. So for the key findings, the key takeaways from those results, as I mentioned, nearly all the targets were met. Those sand filters, which were intended to provide that nitrogen and phosphorus removal, did not perform as well in that cold weather climate. Were a little bit more operationally intensive than we would have anticipated. So those will not be used for the full scale system. That's the conclusion we can draw now. That we feel like we can get that TIN down, that total organic nitrogen we don't need, and keep that full phosphorus low through our treatment with different needs. That third bullet there on the left, we will be looking at a different nitrogen removal technology that maybe treats all of the process stream or a side stream of it after RO to take care of that remaining total organic nitrogen. The example we have here, and one of the ones we're looking at is ion exchange, which is an established technology used in drinking water and wastewater treatment. Top right there, we did meet our 98% recovery target. As Lane clarified and mentioned, the brine minimization, the salt we piloted through IDE, did the job and exceeded that 98% recovery at 98.7%. What we do want to look at, which are brine minimization technologies for full scale design to see if we can get more water recovered above that 98%, 98.7% we achieved, and see how that compares for cost and other considerations as well. The one we did, softening one we did, do bench scale tests on I mentioned earlier, and the preliminary results showed 99, I think 0.2%. So 0.5% higher than what we achieved with the pilot. Yeah, total recovery, thank you. The two RO systems did meet their 90% objective. One of them only for a short time, had to go back to 86%. But yeah, that total system recovery wasn't that. So for some additional purified water quality monitoring from what we presented here, and that's captured in the bulk of the pilot report, we tested 304 other constituents, which 16 were detected, and of the 16 detected, only 11 constituents have established objectives. For the results we got there all of those stringent objectives, and then of those remaining, there was no detection of the remaining constituents that were analyzed. Appendix D of the pilot report has the full results of these. These capture things like the CECs and pharmaceuticals that are obviously a concern for us. We want to make sure we're treating down to non-detect levels of fully stringent objectives.
I just want to add, while we were talking, I verified the answer to your prior question, Rick, about, did it meet all of the drinking water limits? And it does. That's incorporated in the results of these Of those 304 constituents, we did test all of the drinking water limits, and the results came in below the objectives. And that's all listed out in Appendix D of the pilot report, if anyone wants to see that.
In the process of developing the EIR, we've had numerous presentations that talked about the ID process. Well, now we're going to change and use a different process. Is there enough wiggle room in the EIR that changing that process does not create the need for reevaluation?
I believe so. We will consult with the environmental team, as we're going through preliminary design process to get their, CEQA opinion on that. But the processes that we are moving forward with actually produce better water quality than the original process, the phase one process. So, I think the impacts, potentially even be less, and they were already less than significant. So we don't anticipate a CEQA issue or a need to revisit. But we will be talking with the environmental and legal team about any changes that are made to the scope to help them make that determination. And if they determine that additional impacts need to be looked at, it would be a supplemental CEQA process.
As I recall, there was concern, the comments about a baseline type of testing, and they wanted to know more specifically exactly what we were going to be testing for and what standards. And I noticed that you put in here constituents of emerging concern. Now, is that to cover future temps when somebody finally sets a standard for something that doesn't currently? And are we talking things like the forever chemicals that are now showing up in even the ski wax used on the snowboards and the skis on the slopes, and it's ending up in our driveway?
Yeah, that's correct. So it does consider those CECs and PFAS or forever chemicals. CECs are not currently regulated in large part because a lot of them can't be detected or there's no methods for detecting them, but we know they exist. Yeah, those regulations may come. Our next slide will actually talk a little bit about
How do you address it?
that process. Yeah.
Okay.
Yeah, so using forever chemical as an example, Director Walsh mentioned, on the drinking water side, a couple of those compounds were just issued maximum contaminant levels on the drinking water side. So we've been asked the question, okay, we're going to design this process, we're looking at certain constituents. What if we get hit with a new regulation years down the line? What are we going to have to do? Up front, I'll say the advanced treatment process we're employing here with a combination of RO and the UVOP system primarily treats both these pharmaceutical already that we're aware of that we can measure or understand. But say we did get hit with a new regulation, this is just a little workflow and kind of timeline, what we might expect. So using the forever chemicals or PFAS, we'll say on the wastewater side, the regulators side, they want to establish a new water quality objective. We would go to a public comment period. After that public comment period, collecting that feedback, considering it for the final rule, the regulators would issue a final rule with that new objective. And then agencies such as RO would have those new limits added to a monitoring plan, and they would be given a certain amount of time to meet those limits. So that may be less than 5 years, or it could be at the next 5-year cycle of permit renewals. It typically depends on the constituent, the urgency the regulators see for meeting that. If there is an inability for agencies, not just part of any of the California agencies to meet those limits, they may have a compliance plan they'll work with the regulators to establish to make sure they get there in a stepwise fashion, they're making progress. To ultimately be able to meet that limit. The regulators would approve that compliance plan and enforce that limit on some predetermined time basis. So if we get hit with a forever chemicals regulatory objective, it's not, you have to start meeting it tomorrow. Thankfully, with the process we have here, we have pretty high confidence with pretty much all the CECs and pharmaceuticals and forever chemicals that are out there. We're already going to forever chemicals we did test for were all non-detect. Right? Yeah. So for the ones we already tested, we're already non-detect, but you do have some time basis to be able to meet the objectives and get to that point. And that's consistent across the state, because there's a lot of agencies that can't meet objectives that come out, so they have to be given some time to maybe construct a new process or change operations to be able to.
Mr. Sitton, for one, and some other people expressed concerns that we could inadvertently contaminate our ground table. And so this might address further contamination once it's discovered to be a problem. But look at the decades for DDT, now Roundup. It took a while to realize these were problems. And there's no way to avoid accidentally shooting ourselves in the foot. Is there?
Again, I think with the process we're employing here, we're getting past drinking water levels for nearly all these constituents. So I would say, like, after this piece of it, I think we're getting ahead of the game a little bit. In this case, when you're employing an advanced treatment process, that you're already removing a lot of these constituents that either aren't regulated or we're already hitting the non-detect levels. So if anything, I think it may allow us to get ahead of the game for those future potential objectives.
There is no better process than this, right? I mean, that's the whole point is this process, there is no better process. And, you know, what we're employing now and sending down to Lucerne and having that go into their groundwater table, you know, I mean, you have to recognize that that could be an issue is, you know, if we just continue to do what we're doing now.
Do you think there's a possibility that, you know, if they were part of chemical regulations were passed by the state of California, which, you know, in the past, we can kind of have the option, but arguing with the state on whether we should do it or not. I mean, if that would have passed, then actually dealing with private chemicals, we have to either do it through this process or a process that goes to a certain valley. It's like a water table. So I don't know how we escape that regulation, a new mandate from the state and federal government for the chemicals. We don't get a free pass because we move it to a certain valley.
No, you do not, and we would not, and we would still have the same regulations would apply to us down there as well. So you know, when you're looking at those regular chemicals and the state mandates to clean up wastewater for those kind of constituent, those kinds of concerns, we would definitely have the same kind of requirements.
Except that when we started the discussion, it was often said that this is tried and true technology. Mr. Shimon has worked on it. It's been tried other places. And yet now we find out that the sand wasn't such a good idea. And even the IDE process wasn't quite what we thought. So that's why I ask is that there are no absolutes here. And so I'm concerned when we say we can handle it or we'll get into a jump on it and we'll avoid contamination. That's why I'm asking.
I mean, the sand filter was put in place or as part of the process to remove nutrients. Right, and it was a cheaper method than the other methods that we know that are out there. And so that's why it was tried as an opportunity to a more cost-effective method. But again, you know, with the temperature, we wanted to make sure it worked with temperature. It didn't, and so we went a different way. The IDE it performed. They got down to an 86% recovery rate on the RO system. The CCR or the DuPont system, RO system just did a better job and got those some of the constituents that we were looking at down further than the IDE process. But the IDE process worked. It just the DuPont system just worked better. And so that's part of the piloting is to test different pieces of equipment to find out what's the best equipment out there. Again, that doesn't mean that, you know, doing the big process, you know, DuPont's gonna get the bid, but you know, with those kind of criteria that we're going to put in the specifications, the likelihood is a company like either DuPont or equivalent is going to get a bid for the RO system itself.
But it's also true that, as stated in here, this isn't the final plan. And we may have to change some more things.
I mean, the final plan that we're gonna be moving forward with, this is the basis of the plan development. Matt's team is going to move forward with an actual plan to propose what the exact system is going to look at, what we're gonna see in the fall. That's what we'll move forward with.
But it won't be established until the design phase.
Well, we are in the design phase now.
But it,
We are in design and we are in the design phase. This was part of that whole thing, is to show in this piloting what equipment worked and how well what worked. And then Matt takes the results from this and uses it to further establish the exact treatment train that can meet the criteria that we know is from the regional board.
well, then I just go back to the statement that this is not the final word. Things can still change.
Yeah, the only things we anticipate changing are the nutrient removal process, and so we're looking at some modifications, you know, for us existing. The treatment process as well as climate change, and then if we can find a better way to achieve the results that we achieve with brine mineralization, then we may pivot in that direction. So those really are the two themes that we're looking at changing, as part of this, you know, the preliminary design. Television program.
Couldn't you argue though that the test water that was produced and tested is cleaner than the probably water in this bottle that we're drinking?
I can't say for certain, we don't have the water quality results for a bottle we are drinking, however, as we.
Well, most of it's pulled out of wells, right into wells, and then
Yeah.
put it into bottles and shipped to us.
Certainly, the objectives that Barwell will have in their permit are more stringent than drinking water objectives. Which is just a reflection of protecting the existing water quality. So that's how those regulations are designed, that at the time those rules were set, the water quality in Big Bear Lake was very good, and the regulations prevent degradation, basically. And so
So the water could be put in our drinking system if we want.
there are additional regulations for that, so that would be, that would fall under direct potable reuse, right? If you actually were to pivot in the future. There are even more stringent monitoring requirements for that, but it does meet all.
So the question is suppose what the future is going to bring, what the future will bring more regulations. What I'm hearing, the chairman asked, is that would also include the water that you're now sending to Lucerne Valley.
Yes,
So we don't get away from
right,
future regulations.
right. So to Director Welch's point, you know, we cannot be 100% certain right now that any future regulations for contaminants would be able to be removed by the system that's proposed as part of Replenish Repair. Everything we know about now could be, but it is possible that, you know, as science evolves, there could be additional things that come up in the future that we don't know about today.
So then the water that we're pumping out of the ground currently, the CSD pumps out of the ground,
Yeah.
and it pumps out of the ground. These regulations are in place there as well.
So, yeah, and
So there
so,
could be purification process in CSD and DEP has to put in place for future regulation, but we're just supposing that. We're just guessing.
it's possible, yeah. So the regulations typically start on the drinking water system. So they give the forever chemical, that's actually the drinking water regulation. It is currently applied to wastewater discharges. However, because your wastewater in the Stern Valley is being disposed of into a basin that is used for drinking water, it's only a matter of time before that trickles to a wastewater discharge. So even if, you weren't to do this project now, there are going to be many regulatory water quality drivers in the future that you'll have to consider that could cause, you have to do additional treatment because of drinking water regulations.
I just hate to sit here, take time to suppose what might happen in the future.
Right, yeah,
And I agree, there more than likely will be heavier regulations coming our direction. There's no doubt about it. But like what I've heard is that we're a few steps ahead by going through this process now.
yes, this,
And so we're much better off than other agencies that might have to go through this whole process anyways. It's still not going to use their water, they still might have to discharge it.
absolutely, yeah, most plants in the state are treated as secondary or tertiary. And those levels of treatment would not be capable of removing, things like rubber. So Barwa does attain, by implementing a Replenish bigger, you really do get a lot more regulatory certainty into the future than if you, were to stay with your existing process.
I just need to take time. There's a long presentation. We need to take time supposing what might take place, because we know that a lot of things might take place. Just don't know what they are.
Right, everything
Trying to guess at this point is, I don't think, a fruitful discussion.
that we know today it's exceeding all regulatory requirements.
Plus,
Correct.
even more.
Yeah, exceeding.
And we know, hopefully this is correct, we know that the lake itself was not providing any groundwater recharge. Is that correct? Maybe one area that's potentially for that.
They've done a bunch of different studies, and I don't want to speak out of turn for MWE or DWP, but they've done a bunch of different studies on the influence of the wells. The influence of the lake on the existing drinking water wells that surround the lake. And I know there was a couple that they moved specifically because of the influence when the water table, when the water gets high in the lake, they had some influence, but otherwise, my understanding, based on what I've been told from Tom Harder, who's done all the studies for it, there is no influence on the groundwater, the drinking water from the lake itself.
So should DWP move forward with a project to recharge in Sand Canyon, that would require a full brand new set of good complying with whatever regulations in place at that time. So really, we've got a two-step process here in which borrower is required to meet a certain standard, and then when DWP, if they so desire to move forward with that project, but then again, have to meet that standard of recharging Sand Canyon.
Yeah, they have a whole other set of requirements, and Lane knows more about it than I do. For recharging in Sand Canyon. And yeah.
Yeah, and those constituents were all evaluated as part of the pilot report as well, so it's not a different set of constituents we need to worry about. It would be a different permit though, and so DWP and CSU that, the agencies doing the recharge would have to comply with the permit that's under a different part of the regulation than what our has to comply with. But the treatment results meet all of the requirements of that permit as
And they would have a different monitoring requirement, like something separate from us. They have a whole nother set of things that they have to. Environmental review. Compliant process and monitoring would all be something separate for them to comply with.
Which then would give the public an opportunity to address those issues at that time.
Definitely.
All right, only got last couple of closeouts. I appreciate the questions. I should turn my mic on, sorry. So for next steps, what we have been doing for follow-up work, and then we'll be a little bit of the preliminary design report that will include. But I think we've talked about both these points in some of our discussions already, but just to reiterate, we'll do some process modeling for on-exchange for nitrogen removal. Again, an established technology, as will the sand filters. Director Walsh, you asked about that. Is that cold weather climate that has been limited us. They're typically rated down to 10 degrees Celsius. Baker had quite a cold winter. We got down to 5 degrees Celsius, so we saw some limitations there. Operational intensity was also another factor there, why we would recommend that. So we'll be looking at those alternatives, and for item 2 there, again, that brine minimization alternative analysis, we've already completed the bench scale testing of the softening process, using brine directly CCRO pilot, shows that RO system during phase 2, and we were able to achieve over 99% total system recovery, shown on that one, which would replace that ID brine minimization salter. We'll be looking at the results of these analyses, including those in the preliminary design report, which is expected in fall of 2024. We'll have a full comparison of the different brine minimization processes and what it means for downstream brine management infrastructure as well.
Question for Code.
Yeah,
I know water softening, is that the same process that we're talking about? It says softening.
for the purpose of this discussion, yeah, it's the same process.
Isn't softening sort of a salt sodium?
Yeah, in this case, it's using lime softening, so.
So it attracts sodium? Does it not? If you could just explain a little bit better in case.
Yeah, the lime basically helps remove additional dissolved constituents that would scale up a downstream RO membrane. We actually do have a slide showing the process. I can skip you out for this last slide if that will help. But basically, we're trying to, the whole game with reverse osmosis is how much can you push through it without scaling or fouling the membrane, because that's what limits its ability to actually produce that water at the target recovery you're trying to achieve. So the softening adds lime and produces basically a sludge that you could divert to the existing belt rest would actually, excuse me, improve the waterability of the sludge, get it to a higher percentage than what we do now with the existing belt rest. And then that clarified water you get off the top would go to a secondary RO system that gets you that 99.2% recovery.
Okay, thank you.
So for the preliminary design report. Correct, yeah, so that another advantage of that is the higher percentage of the sludge, it also reduces the sludge hauling cost with more concentrated soil solid, so it provides additional benefits to the O&M. So the preliminary design report, summarize everything we talked about here, those additional next steps and those alternative analyses we just mentioned in the last slide. The top there is just really illustrating that we had a facility plan through the planning contract, and then a design validation report through the design contract. It does make more sense to combine into a PDR, and it's less effort and time for us to do that. So we have it broken into 3 parts that may be phased for review for the agency team. So part 1 will have the introduction to the program, highlight the benefits, background of the regulatory analyses we performed. Part 2 is basically what the facility plan was, a lot of the engineering work, what technologies that we look at, what do we do for piloting, what were the findings from that. And then part 3 is more design focused, the recommended projects, the treatment train we recommend that we are confident can hit these limits or exceed them. And then an updated cost estimate, along with some preliminary design criteria and implementation plan, which is, how do we get from point A to point B on a timeline and contractual mechanism, et cetera. So that cost estimate point in the PDR, fall 2024, I imagine would be, David, I think you mentioned earlier, another kind of pause point in discussion with the board.
Yeah, so we'll be able to present back that design validation report to the board with an updated cost estimate. That will give you the board a better idea of where we're at and what the overall cost of the project is gonna be based on the recommended design.
That concludes the discussion and questions. If you have any further.
Yes.
Is it normal for this equipment to have the indicated breakdowns because it was a pilot program, or is that inherent in the equipment?
More of the pilot program, so all the systems excluding the sand filters really operated as we expected. There's always challenges with pilot because you're not bidding out contractually, setting responsibility for a contractor to make sure everything works as intended, as rigorously as it should occur. Not doing that as rigorously for a pilot. We're trying to string together different processes, simulate a treatment train. Pilot inevitably happens more issues because you don't have the level of integration you have in the full design as far as the different treatment technologies communicating to one another. It's more robust for a full scale system, but as far as what we're able to simulate and achieve for treatment, again, I think we mentioned earlier, we're confident that the results we get here are what we'll get at full scale, if not better at full scale. So the sand filters, I knew as an engineer going in that some operators load them and some operators never have issues with them. It has a lot to do with the manufacturer, the water quality coming in, how well they maintain it, and then in our case, the temperature. There's also some dimensional differences from pilot to full scale for sand filters that we felt like maybe caused some of those issues, but for everything downstream operated as intended, aside from, minor hiccups that are anticipated in the pilot facility.
Well, they talked about the UV light. They couldn't get it to respond directly, so they left it on 100%.
Oh, yeah, so you're talking about the performance test. So yeah, that was, specifically testing the specific breakdown of CEC through more rigorous stuff than just operating the pilot and doing our routine weekly monitoring. So yeah, that would not happen at full scale. For instance, you would have warranties or a technician on call contractually through that supplier. Trojan's based out of Canada. We started that and it's in the evening, we can't necessarily call or have a patch in through the network to correct that. So we just have to run with keeping it at 100%, which is a conservative basis. In full scale, you would have to do that performance test again for the regulatory agencies as part of startup. And that's where you bring down that land power and you may actually be able to use less energy to achieve the same level of treatment that we looked at for that performance test.
Is that also why they were having to turn things down at night and then bring it back up by day?
You're talking about the UV system in particular?
No, but there were other references to where they were reducing numbers for a night run and then back up by day.
I think one of the points in the pilot report that looked at the specifics was the oxidant, which is the hydrogen peroxide or the bleach. We would turn that off prior, like in between sampling
It's
events.
because they had a leaking tank too. I don't know if that's the same one.
Oh, okay, yeah, so the pilot systems, frankly, I mean, they travel from state to state, they get banged around, they're traveling on the back of the truck. That's why I mentioned in pilot system, you would inevitably have some issues pop up. So yeah, for a full scale system, not only would they be warranty, to spec and more robust, but you're not gonna have those kinds of issues you have in the pilot.
Hopefully.
Yeah, but based on the full scale systems we have and the specs we would have, be much more robust. That's incidents and failures. We also have redundancy, so if one train or piece of equipment is offline, there's another one to pick up the slack.
My questions? Okay, your presentation.
Thank you, Mark.
Thank you.
Just received.
Yep.